Hello, this is Charlene. This video is an introduction to normal distributions. Previously in Chapter 6, we looked at binomial distributions. Binomial distributions are discrete, but this is Chapter 7, and we're going to be looking at continuous probability distributions called the normal distribution. What's the difference between discrete and normal? Well, if you're thinking about values, x values, the discrete values are countable. So all of these little dots right here would represent x values that are countable, 1, 2, 3. So binomial distributions have discrete values, but the continuous probability distribution has a lot of values along an interval. It can be things that are measured, things that are not individual values. So it's going to be a range or an interval. Another way to say this is a normal distribution is a continuous probability distribution for a random variable x. The graph of a normal distribution is called the normal curve. We can sometimes think about this word normal as in generic or general or standard. When you're taking other math classes, a lot of times you have like standard formulas, and it's kind of a generic, general formula. So that's kind of what this normal curve. It's a little bit generic in nature at first, but then we're going to use it for specific real life applications later on. Let's talk about the properties of the normal distribution. Make sure and read through this entire list um, on your own time, but we are going to focus on the highlights. The normal curve is symmetric, about the mean. Here is the mean, it is in the middle, and there's an invisible line of symmetry, which means that on both sides we have mirror images of each other. Okay, we also have the idea that the mean, the median, and the mode are all equal to each other. So because the mean here is also the median, which is also the mode, that means that we're going to have this single peak. Okay. And then we have the normal curve has inflection points. The inflection points are listed right here. I got an inflection point right here and right here. They just happen to line up with the first standard deviations on both sides of our curve. So there's the first standard deviation below the mean, and here is the first standard deviation above the mean. So the inflection points are the same as the first standard deviations. Okay, we also have an area under the normal curve is equal to 1. So all this blue area adds up to a space or an area equal to 1. So the area, and of course the area is a value, right? The area is about space. So it is equal to 1. That's going to come up over and over again. It connects back to the idea that probabilities always add up to 1 or 100% of something. Okay, so we have also the idea that the right side equals the left side. So this right here is exactly half, 50%, and this half on the right side is also 50%. We also have this little section right here. This is a very interesting section, and I want you to remember this, put a little star by it in your notes because we are going to be coming back to that with one of our applications. But it's this idea that it says that the graph never reaches the horizontal axis, either on the left side or the right side. And you can kind of see that right here. Here's the graph, the little black part of it. But if you notice, it's above the x-axis. It's not crossing the x-axis. And same thing over here. The graph is just a little bit above the x-axis. It's actually not touching the x-axis. And it says that it is going to, as x either increases or decreases, it's actually never going to reach the x-axis. It will never cross the x-axis. So that's an interesting concept. Okay, and then also the empirical rules, the 68% in the middle here. Let's see, let's find a different marker here. Yeah, this is the 68%. this is 68%. And you got the 95%. So the 95% is within 2 standard deviations. And then you have the 99.7, which is within 3 standard deviations. So that is going to be applicable to the normal distribution as well. The normal curve is graphed using this equation. At least that's what the textbook that we are using says. But when I put that equation in here in the TI-84, and I also put that equation in here in Desmos, well, it gave me this graph right here. That is not a normal curve. Normal curve needs to look like that. So I found this other one that's a much better setup. I don't think that they are very clear on what, needs to be done first, what needs to be parenthetical. So it's not really clear. Because if you notice, this one right here, I mean, this one is like almost identical to what they've written there. Now, if you notice, I also have the mu. The mu is in the middle, and it's going to be equal to 0. That's the generic standard general form. And your first standard deviation is going to be equal to a 1. So those are the numbers that I put in here. I put in a 1 for the standard deviation. I put in a 1 for the standard deviation there, and 0 in for the mu. And so that's exactly what I did here. Got a 1 right there, a 0, and a 1. Okay, and like I said, it did not give us what we wanted. It gave us this kind of an exponential curve, not a normal probability curve. But I found this version of it, this version of the normal curve equation. This one is a much better setup. This piece right here is where we needed to change it up. So I rejected this setup and I replaced it with this setup. And when I did this in the TI-84, I did it right here. Kind of cut it off right there, but this right here is just identical to that piece right there. So anyway, but I changed up this exponent part of the E. Okay, when I did that, here's what happened. I got this nice curve, up, over, curve. And the same thing here in Desmos, I also set it up that way. I used this exponential version that looks like this, and it gave me a nice curve. Yeah, so anyway, I just wanted to talk about this briefly because I don't like the version of this. I don't think it's clear how to set this up. So I reject this version. I reject this version, and I would replace it with this version of the equation. It should be the same equation, but something is not right about that one. It's too hard to interpret what needs to be parenthetically addressed with it. Normal distributions can be used to model many sets of measurements, such as human physiological measurements like height, weight, and volume, standardized test scores like SAT or ACTs, measurement errors in scientific experiments, IQ scores, manufacturing quality control data, that might include like defects in production, and human blood pressure. So those are just a small sample of the types of real life situations that normal distributions can be used to model. The mean and the standard deviation of the normal curve will determine the shape of the curve. Specifically, the mean will always be in the center of the curve where the line of symmetry is located. And as the standard deviation increases, the curve will spread out and flatten. So here's three examples. Here are three curves. I've got a standard deviation of 1.5 on the first one, standard deviation of 0.7 on the second one, and a standard deviation of also 0.7. So if you notice, the largest standard deviation is 1.5. And what has happened to the curve? The curve has flattened out. It is shorter than the other two. So it is flattened out and spread out. That's what happens when the standard deviation increases. When it gets larger, it flattens the curve and spreads out the standard deviations. So this is an example to help us understand how the mean and standard deviation are related to the normal curve. Our question says, which normal curve has the greatest mean? Well, on curve A, the mean is right there in the middle. So that's about 45. So 45. Okay, and then we've got curve B, and its mean is right there in the middle, and it's at the 60. So 60. The mean of curve B is 60. And then we have the third curve C, and the middle of it is also at 45. Also at 45. But the question is, which normal curve has the greatest mean? Well, that would be curve B. Curve B has a mean of 60. Our next question says, which normal curve has the greatest standard deviation? Which is also like asking ourselves which one spreads out the most. The biggest standard deviation will cause a flattening and a spread of the curve. So it looks like the one that is the shortest and is also kind of spread out would be curve C. We're now going to start talking about how the standard normal distribution is going to help us be able to find areas and probabilities. The standard normal distribution has three primary properties that are always true. The graph is bell-shaped, the mean is equal to a 0, and the standard deviation is equal to 1. When we worked on the empirical rule graph, we always had data, right? This was data points on the x-axis. This right here, 74 through 88, this could be like test averages, like the average test score could have been an 81, and that was real data. But on our standard normal distribution, we are going to defer to the mean always equaling zero, and the standard deviation is always going to be equal to 1. So we're going to have 0 here, 1 and 2, and -1 and -2. So the standard normal distribution will always default to these numbers, and we'll talk about what those mean later. We've actually talked about z-scores before. So if you remember the z-scores, those are z-scores. So z-scores are related to standard deviations, right? And so that makes sense because we've got the standard deviation is equal to 1. So there's a standard deviation equal to 1. And that is the first standard deviation above the mean. And this -1 is the first standard deviation below the mean. Okay, so but let's go back to the empirical rule graph and think about this for just a second. We always had percentages, right? The empirical rule. If we add up all of our percentages, we can remember that they all add up to 100%. We also talked a lot about the fact that the number that 100% is equal to is 1. So that brings us back to our standard normal distribution because all of this area on the empirical rule graph adds up to 100% of the area. But all of this area underneath the curve for the standard normal distribution, it is going to be equal to 1. So there's a relationship there. There's a 1 here, and it's related to the 100% that's in the empirical rule graph. And of course, down here, you see that they've made these correlation with these numbers on this empirical real graph as well. I just want you to be aware that a lot of times these ends on these graphs are slightly different from one website to another. If you notice, this one is like 2.35 and 0.15%. This one is 2.35, and they don't even acknowledge the 0.15%. On this one, they actually combine or round 2.35 to 2.4, and they completely ignore the 0.15. So just be aware that some different websites, different textbooks use slightly different notation for these ends. That's our unusual or outlier space is on the ends, and just be aware that those are out there and just don't let it confuse you. If you have questions to answer, pay attention to any graphs that they want you to use and the numbers that are on the graphs that they want you to use. So just don't be confused by that. And of course, the one that I used above actually had 2.5% for the entire ends. Both ends had 2.5%. So they went ahead and added the 2.35 and the 0.15 together to get a total of 2.5%. So anyway, just want to make you aware of that and just don't let it confuse you. Because the total area under the curve is equal to 1, there is a correspondence to the area and the probability. So, like I said, the total area under the curve, so here's the area of the standard normal distribution curve. If you add up all these numbers, which are basically converting the percents to decimals, it will equal 1. So this side was equal, if you add up all the percents, it equals 100%. But essentially, you could see that the area is equal to the probability. Okay, we're going to discuss the connection between the area and the probability. It says that the area to the right of the z-score A. So there's a z-score right there, like -1. It's on the left side, the negative side of the standard normal distribution. That's a z-score. And it's saying the area to the right of that. So that would include all of this space. All of this space would be the area. Oops, I'm kind of going outside the lines, but that's okay. So all that area they're calling A. Okay. And they say that that area is equivalent to the probability the z-score is greater than A. So we write that like the probability that z is greater than A. And they're saying that it is equivalent to the area. So that means that the area, all of this area, all of this area in the pink is equal to the probability that z is greater than A, because we have a z-score -1 right there. So it would say that the area is equal to the probability that -1 is greater than that area. Using the same reasoning, we can now say that the area to the left of the z-score is equivalent to the probability the z-score is less than A. And of course, we can write this in this manner. The probability that z is less than A. So here is our z-score. We're saying to the left of that. So that means we could consider all of this area to the left of that z-score. And all of that area right there, all of that area is going to be equal to the probability um, that z is less than A. So the area is less than the z-score, and it's equal to the probability that the z is less than A. Like I said, you'll get used to understanding that and hearing that going forward. It'll make more sense as we put it into action. The area in the middle of the z-scores, A and B, is equivalent to the probability the z-score is between A and B. So if we have two z-scores, A and B, let's call these -1 and 2, we can write this probability, the probability that -1 is less than the z is less than the 2. So it's between those. The z is going to be in between those two things. The area is going to be equal to that. The area is going to be equal to that. So where is the area? Well, the area would be between those two things. So all of this area is going to be represented by the probability that the z is between -1 and 2. On the standard normal distribution, 0 is always in the middle. It's always the mean. The mean is 0. So on the standard normal distribution, anything less than the 0, which is on the left-hand side, will be have a z-score of 0, and the area will be 0.5, which is 50%, right? So this is 50%, but in decimals, that's equal to 0.5. And also on the other side, z-score, the probability that the z is greater than 0, well, that's on the right side. That's the area to the right side. And it is also a z-score of 0, but the area is also 0.5. So this is 50%. But in terms of the standard normal distribution, it is equal to 0.5. So 0.5 area on the left side plus 0.5 area on the right side is equal to a total area of 1, which we've already been told is the standard normal distribution rule and property. This next item is about notation. It says the notation z sub alpha is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. Okay, so let's think about this. It's telling us that z sub alpha is equal to alpha, but it's also telling us that the area is alpha. The area to the right is alpha. So that means that we could actually rewrite that as z sub alpha is equal to the area to the right. Well, if alpha is equal to the area to the right, that means alpha has to equal area to the right in both places, right? So the z sub area to the right is equal to the area to the right. You see how you just got to understand what it is they're saying in the English sentence. So the z sub area to the right is equal to the area to the right. So if we have the z-score right here, if I had that z-score, and let's say we have z sub 0.25, well, 0.25 represents the area to the right. So that means that the area to the right of this z-score would be all of this area, and it would be equal to 0.25. That area would be equal to an area of 0.25. Okay, so I hope that makes sense. The z sub 0.25 is equal to the area to the right of that z-score.